We've seen that when a magnetic field lies along the direction of the velocity of a positive charge or a negative charge, the force will be zero on that charge. F is zero here because of our cross product relationship involves the sine of the angle between B and B. Here the angle is zero, sine of zero is zero, so no force. If you have a charge, let's say moving upward in a region of space where the magnetic field is in, shown by this X, if you use the right-hand rule, fingers in the direction of V, pointing up, curl towards B, pointing in, thumb points to the left, that's a force then that points this direction. So if you were moving up and get pushed over, you'll start to bend this direction. And this results in circular motion, because if the charge was up here, its velocity would be this way, tangent to the circle. V, curl B, thumb is down. You always end up with an inward pointing force. So when V is perpendicular to B, Q moves in a circle, as we've seen in the PowerPoint as well. But what happens if V and B are not perpendicular or parallel? So let's look at that case. Here's a positive charge, let's say that's moving in this direction at velocity V. And let's say it's in a region of space where the magnetic field points this direction. Okay, this is a non-90 degree angle, so we're not going to get circular motion. To figure out what's going to happen, break the velocity vector into components. One component of the velocity vector is perpendicular to the magnetic field. So this is a right angle, and I'll label that V perpendicular. Another component of the velocity is parallel to the magnetic field. I'll draw that like this, and I'm labeling that V parallel, two parallel lines. Okay, so I broke the velocity into components. Well, we've seen when V is parallel to B, there's no force. And we've seen when V is perpendicular to B, the charge moves in a circle. So what results for the motion here? Well, if I use my right-hand rule for the perpendicular component, fingers in direction of V perpendicular, curl towards B without breaking your arm, thumb points out. So there's a force out here. I'll put a dot with a circle and say F out initially. Okay, so the charge, the perpendicular part of the velocity says go that way, but it's getting pushed out. So it's going to start curving out. But it still has this parallel velocity which points up. That doesn't feel a force from the magnetism, but that velocity is still there. That momentum is still there. So you're going to go in a circle due to V perpendicular, coming out of the board first and then in, but you're also going to get dragged up by V parallel. This results in a spiral path along the magnetic field vector. So this charge is going to spiral up along B. You get helical motion or spiral motion here. This is the general motion you get when V and B are not perpendicular or parallel to each other. The charge will always spiral along the magnetic field line one way or the other. It could go the opposite way if the angle between V and B was greater than 90. It'll spiral in the opposite direction of B.